So on Thursday of last week then, or Wednesday, I said Thursday, but on Wednesday, in fact, we learned about one of the two ways we can make a compound, which is like sodium and chlorine. We can give away electrons and take electrons. And then what holds things together once we've given away electrons or taken electrons? Why do they actually stick together? Because they become charged. And once something has a charge, opposite charges attract. Guys, thank you. But I want to look at a second example, which is chlorine and fluorine. So I'd like you to take a minute and draw a Lewis structure of chlorine over here and a Lewis structure of fluorine over there. If you've already done your Lewis structures, you can just copy it over. And you can draw them nice and big. Doesn't matter. And just one of each. Okay, like this. Now, how do I make a Lewis structure of fluorine? Yep. Sure. And in fluorine's valence shell, how many electrons does it have? How would I know? Yep. Good. It's in the 7th column, and I could just count over, right? So I could go 1, 2, 3, 4, 5, 6. There's fluorine at 7. Good. And 1, 2 makes no difference which one you put first. All right. How's that look?
Pretty good.
All right. And what about chlorine?
Same thing.
Oh, don't sound so disappointed. All right. Yeah, I picked two atoms that actually have the same electron configuration. Now, here's my question. Do you think it would be convenient for these two things to bond by giving and taking electrons? And if not, why not? Yeah, they're in the same family. They have the same number. Yeah, they both need electrons. Does either of these want to give away electrons? No. They are both, the word we use for it is actually electronegative. You don't have to know that. But what it does mean is this. They're both really electron hungry. They both are trying to pull in electrons. So if fluorine only needs one more electron, it's not about to give it away. Does that make sense? And likewise, if chlorine only needs one more electron, it's not about to give it away. Does anyone play, I never have, but like the McDonald's Monopoly thing? No? Yeah, I know when I get a coffee, sometimes you can peel the little things off and you get the slips. But I imagine that if you had like all the things you needed except for one, and somebody else had all the things they need except for one, and you had the one the other one needed, you'd never come to an agreement of who was going to get it and who was going to give it away, right? Like you'd just fight, and eventually like it'd just be like, I'm not talking to you anymore, I'm not talking to you anymore, I hate you, and so on and so forth. So chlorine and fluorine both want to get electrons. And I'm going to put want in quotation marks so as not to anthropomorphize these more than necessary, but they both want electrons. Neither wants to lose electrons. What then could they do? Let's say let's say hypothetically that I collect comic books. Hypothetically, of course. Hypothetically. And let's say hypothetically I collect like the like the post Jack Kirby era X-Men. Just hypothetically again. Like everything from 96 up to maybe 245. Again, like just imagining this. So let's say that's my collection. And the only thing I'm missing is Giant Size X-Men #1, which is a classic, by the way. The only book I'm missing. All right? I'm trying to, okay, who out here looks remotely like they might also. People don't really collect comic books as much as they used to, right? When I was a kid, it wasn't cool to be into this stuff. So you could tell anyone who had like bruised face on a daily basis, they were comic book collectors. But now it's like lots of people collect comic books.
Leave Richard alone.
We don't point. So anyway, so let's say that I have my comic book collection and Deanna Zinger. Why did I call you Deanna Zinger? I talked to her like 4 years ago. Sorry about that. Deanna Rutledge also collects comic books, also is into the post-Jack Kirby, post-Stanley X-Men, right when they hit the force. And she's missing just issue 105. So we're both missing one comic book.
Is 105 rare?
In the middle of the road. But like if you want like a nice condition one, it's pretty rare.
And then you have a rare one?
Yeah. Yeah, we're both missing something really rare. We can't find it anywhere. What could we do? Am I ever going to convince her to give me the one that I need?
Yes.
No. Is she ever going to convince me to give her the one she needs?
No. Trade.
We could trade, but then we'd still both be missing one. We'd just be missing different ones. But what if we said, okay, here's the deal. These two books, you're missing one, I'm missing one. What if we said, okay, these two we are going to share? Yeah.
So you guys can just take the book for like a split second, take a picture of it, post it on Google, and it looks like
This is such a high-tech thing. You know, when I was a kid, you know what Google was called? Owning a comic book. Yeah. There was no Google. You know what Snapchat was called? A Polaroid camera. All right. So it was a different world. So here's what we could do. We could combine our collections. We could say these two comic books are going to be part of our shared collection. And now we kind of both have both of them. Does that make sense? Now, it's not perfect because I only have both of them sometimes when I have them. And then sometimes I have neither of them because she has them. But does that make sense? What we could do is we could share. And this is what electrons can be done with as well. So here's what they could do.
I mean, or you could just give me it and then I steal it.
Never. There's a wonderful Simpsons episode about this very, very topic.
if it's a Lewis diagram, do you put them like together? Like,
so here's what's going to happen. They are going to put these two electrons together. They're going to make this a pair of electrons. And those two electrons aren't going to orbit one of them. They're going to orbit both of them. Does that make sense?
yes.
So they say, okay, chlorine looks and says, these two electrons are mine, these two electrons are mine, these two electrons are mine, and then these two electrons are ours. So these two orbit just chlorine, these two orbit just chlorine, these two orbit just chlorine, but these two orbit both of them. And then these two orbit just fluorine, these two orbit just fluorine, these two orbit just fluorine. Now, yes?
How reactive?
This will happen. This is reactive. This is when you put things together like this. Now, they're not as strong as ionic bonds, so the reactions aren't as strong as ionic reactions. But listen, if electrons are going to orbit both atoms, what do those atoms have to do? Can they be really far apart?
No.
No. So the two atoms, to have the electrons orbit both of them, the atoms will have to come close together. And that's a bond. So, fluorine and chlorine will share one pair of electrons. They orbit both atoms. Now, is any atom giving away an electron? No. Is any atom gaining an electron? Are there any charges involved? No, because nothing is gaining, nothing is losing. So the only thing holding them together is the fact that the electrons need to orbit both atoms. So it is this bond that holds them together. You can think of it this way. My sister and I used to share a car. And when we lived in the same house, that worked pretty well, right? Yeah, sure. I mean, she's tougher than I am, so she got the car a lot more than I did. But we shared the car. But when I moved out and I lived in a different house, does it work to share a car at that point? No. You have to be close together to share something, right? So the reason they stay together is because if you're going to share electrons, you have to be close together. We call this...
Let's say shake or share?
Share.
I put shake. I put share.
This is called a covalent bond. Covalent, which is kind of a sciencey sounding word, but let's break it down. What does co mean? Together, yeah. If you cooperate, you operate something together. If you, I'm trying to think. Oh, if two things cohabitate, they live in the same habitat. They are in that habitat together. If you, I'm trying to think of another one. Geez, I'm coming to a blank. Usually I like write things like this out beforehand and then I have good ideas. Anyway, so covalent just means that these two atoms now share two valence electrons. Does that make sense? So covalent means together, sharing. Valent means like valence electrons. It literally means the sharing valence electrons. That's what the name means. So this is called a covalent bond. It's the other way to hold two things together. With that in mind, I want you to see if you can do the same thing for carbon dioxide. Carbon dioxide. So I want you to draw a Lewis diagram for carbon and a Lewis diagram for oxygen.
CO2.
Yeah, we'll get there. We'll get there. So draw a Lewis diagram of oxygen and a Lewis diagram of carbon.
It's a CO right there.
That's cobalt. That's a different thing. So don't use cobalt.
No. I didn't know.
Okay, so let me start with carbon. What's a Lewis diagram for carbon look like? What do you think? Yes, ma'am. Good. And typically, where do we put those? Yeah, very good. And then what does oxygen look like? Yeah, Deanna, what do you got? Great. And so I would normally do 1, 2, 3, 4, and then start doubling up, right? And I'll double up there and there. Doesn't matter where you double up. Okay. Now, I'm going to tell you right now that these make a covalent bond. We'll talk about why later. But there's two things that could happen here. Carbon could give its electrons away. What kind of bond do we call that again? And they give electrons and take them, and they get charged. That's an ionic bond. But that doesn't happen here. This is going to happen by sharing. Okay? So this is going to be covalent. But how electrons can carbon and oxygen share? Yeah, just 2, right? So let's look down here. Carbon needs how many more electrons? It needs 4. Oxygen needs how many more? Just 2. So oxygen is only going to share 2 with carbon. They'll share 2 pairs like that. These are shared electrons. Now, oxygen is happy because from its perspective, it has how many electrons? Yeah. 2, 4, 6, 8. Oxygen is happy. But right now, how many electrons does carbon have orbiting it? It has 2, 4, 5, 6. It still needs how many more? 2. What could I do? I could add another oxygen. Good. Now this gets a little messy. And so sometimes we will draw it where we replace all of the shared electrons with just a line. I'd like to make that a little more definite. Give me a sec, sorry. Just so you know, you'll sometimes see it drawn like this. They sometimes will draw all of the shared pairs as lines. Now, does carbon have any electrons that aren't shared? No. But does oxygen? Yeah, how many? 4. So we could draw this like that, where the lines represent shared pairs, and then we draw in just the electrons that aren't shared. I'm okay with either of these. If you want to draw the circles around it so we can really see where the electrons come from, that's fine. Or if we prefer to draw it like that so it's neater, I'm fine with that too. Again, you don't really, knowing when to use which one is a grade 10 question. So for now, you can use either one you want. Does anyone have any questions about that? That you can share electrons. And again, remember, the electrons that we've circled, those will orbit both of those atoms. So these 2 electrons here don't just spin around carbon. They don't just spin around oxygen. They spin around both of them. Yes, ma'am. Okay, so the ionic bond would work. And it's actually the topic of our next question. Which bond? So it's a great question. Here's the rule. As a rule of thumb, I was trying to come up with a clever James Bond pun to make the title of this, and nothing came to mind. So maybe next time. As a rule, metals give away electrons. Non-metals do what? Yeah, non-metals receive electrons. And I'm going to use the word gain, but so, for an ionic bond, one of the atoms has to do what? Good. And the other one has to be? Very good. So if you have a metal plus a non-metal, that will be what kind of reaction? Or what kind of compound, rather? Very good. So if you put a metal and a non-metal together, they're going to make an ionic compound. The metal will give away the electrons. The non-metal will receive the electrons. But if I put together a non-metal with a non-metal, Now what kind of compound will I get? Very good. This will give us a covalent compound. Yeah. Metalloids are interesting because they can sometimes behave like either of them, which is why for the purpose of this course, we're just going to kind of avoid them. They have interesting behaviors because sometimes they behave like metals and sometimes they behave like nonmetals. So they make it confusing. They can kind of do one or the other, depending on how you work with them. Is that a fair answer? Ah, very good. If you do a metal and a metal, they will not make a compound. They won't, very good. They won't make a compound. Instead, they'll make an alloy, which is just a what? Yeah, but this is just a solution. They just mix together. Remember, a solution is a kind of mixture. So that's actually really interesting, because if you mix two metals together, you can actually always unmix them. You'd have to melt them and put them into a centrifuge and make them separate out, but they don't actually react. So if you mix gold and silver, you'll get an alloy, but that alloy is just those two things mixed together. If you melted it and let the heavier one sink to the bottom and the light one float to the top, you could separate them perfectly. You know what actually, have you heard of a centrifuge? So no problem. A centrifuge is just this. You would melt them, and then you just put them in a machine that spins them really, really, really fast. And when you do that, they like those things will go like this. And spinning it quick, the heaviest thing is going to want to move to the bottom, and the lightest thing will move to the top. We do that like when they take a blood sample. I wish we could still do this. But if you take a blood sample, if I or anyone else teaches you grade 11 biology, we use fake blood. But if you take blood, which is all a mixture, right? It looks just all the same throughout. And if you put it in the centrifuge and spin it, all the red blood cells collect at the bottom, and then you actually get a pure, clear liquid called plasma. You get just the watery part of your blood separated right out, and they call it plasma.
Plasma is something else. Liquid plasma?
Yeah, it's a bad word because it doesn't mean the same thing as plasma, the state of matter plasma. Different thing. Okay. Shh. We have time? Oh, we got lots of time. Look at us. Okay, now. Here's the interesting thing. Ionic bonds, a metal and a nonmetal. Oh. Thanks. Okay. When we put a metal and a nonmetal together, it's really boring. They can only come together one way. Because the metal always gives all of its electrons away until it has an empty shell, and the nonmetal does what? Ionic bond, the one we learned about on Wednesday. The metal always gives all of its electrons away, and the nonmetal always receives them. Does that make sense? But all the interesting chemistry happens with covalent bonds. All the complex stuff that makes you up, all covalent bonds. Because covalent bonds are like Lego. You can put them together any way you want. You can make it bigger and bigger and more complicated and more complicated. And the only rule you have to follow is when you're done, everything has to have shared enough electrons that it has a full covalent shell. And as long as you follow that rule, you can put them together however you want. So I want to take a look here. I put just all the nonmetals and some of the metalloids from the periodic table on here for you. So let's talk first about this group. What do we call this group?
Noble gas.
The noble gases. How many electrons do they have in their outer shell? They have full outer shells. So how many electrons is helium trying to share? None. What about neon?
None.
Argon?
None.
Good. So we're going to put in this table how many bonds each one wants to make. And helium, neon, argon, krypton, xenon, and radon, they all have no desire to make any bonds because they don't need any more electrons. And remember, electrons are what chemistry is all about. So if you are building complicated shapes and complicated structures, you have essentially no neon, argon, krypton, xenon, or radon in you. You're not built of that because you can't build anything out of it. Does that make sense? Very boring. What about fluorine, chlorine, bromine, iodine, astatine? They're all in the second to last column. How many electrons do they need to be stable? Just one. So how many bonds will they make? Yeah, they're only ever going to share one pair of electrons. All right, see if you can fill the rest of this out. Okay. Oxygen, sulfur, selenium, tellurium. What do they all have in common? They need 2 more electrons. So how many bonds do they want to make? 2. What about nitrogen, phosphorus, and astatine? Yes, ma'am. Yeah, they want to make 3 bonds because they need 3 electrons to have a full shell. And? Yeah, very good. And carbon and silicon want to make 4. Now, shh, quiet down. This is really interesting. The backbone of all the compounds that make you is carbon. And carbon is really useful because if I draw just the bonds, if instead of drawing the little dots, if I just draw the bonds, how many bonds does carbon want to make? It wants to make 4. What could I put on any of those bonds? What could I bond it with? Anything I want, right? But potentially I could bond it with another carbon. And how many bonds does that carbon want to make? 4. What could I put here? Another carbon. How long could I make this thing? You have inside of you, for example, your DNA is a good example. Your DNA is millions of carbons long, all strung together. It's a bit more complicated than that. You'll learn all about it in grade 11 biology. Do you do DNA? Yeah, like your nitrogenous base and your But you can make chains of this that are incredibly long. Keep in mind, your cells are all so small you need a microscope to see them. But if you took the DNA in your cell and stretched it out, how long do you think it is?
A mile.
A mile? No, not a mile, but about 2 meters. Every one of your cells has like 2 meters of DNA in it, even though every one of your cells is tiny. It's just coiled up and strung together. So carbon is interesting because, and if I wanted to have this make not just a chain, but a chain that had a branch on it, I could start putting carbons here. Does that make sense? Now, if I wanted this to just stop like that, what could I put on all of these that would make them just stop? Something where it wouldn't keep going. Well, helium won't even make that bond, but you're thinking right. Shh. Whoa. Shut up. So helium... No, you're not. Helium's the right idea. We want something that'll stop it, but it's got to be able to at least connect to it. Yeah, fluorine would work. What else would work? Chlorine would work. What else? What do you think? Bromine would work. Shh. What else? It's iodine. Iodine, yep. That's okay. Yep. What else? Astatine. And I'm actually going to mention one more, which I want you to draw in here. Even though it isn't actually on this side of the periodic table, what's the other thing that wants to make one bond? Hydrogen. Very good. Hydrogen also likes to make one bond. So we could cap all these guys off with hydrogen as well. In fact, hydrogen is like the universal cap. It's what we use to stop these things from keeping to grow in real molecules. So you are made mostly of carbon, hydrogen, and oxygen. for this reason. Now, you will have noticed, if there's a bunch of different ways I can put these together, the naming for these has to be a bit more complicated. You don't have to know the naming till grade 10. I'm not going to test you on it. On the other hand, since we use a lot of these names every day, it doesn't hurt to know the naming. So if we go back to this example, what was this thing called? Yep. Oh, no, but just the, you're totally right, but just the thing. Carbon and 2 oxygens make something called?
A covalent.
Yeah, but just the name of the thing. What is it? Carbon dioxide. Good. You were right, by the way. It is covalent. But yeah, carbon dioxide. What does that name tell me? That they're put together. But what does that di mean? What do you think it would be called if it was carbon and just 1 oxygen? You've probably heard of this thing before. Carbon and just 1 oxygen would probably be called carbon monoxide. So we use a little prefix to tell us how many of everything there is. So what's the prefix for just one of something? Yeah, so mono. Yeah, mono means 1. So monoxide means 1 oxygen. What is the for 2? Like in what? Di. Good. No E, mind you. You're not telling me to die. Just DI. What about 3? Does anyone know?
Try.
Yeah, like when you were little, your first bicycle probably wasn't a bicycle. It probably had 3 wheels. It was a tricycle.
It's like those little cars. It's like
4 is tough. I don't know if anyone will know 4. You think quad, but they don't use quad. They use a weird one that you've probably never heard. Tetra? Okay. And again, I'm not going to test you on this, but what about 5? What do you call a 5-sided figure in math? Penta. Very good. 6 comes after 5. I know my counting. Don't judge me. Hexa. They actually use hepta for 7. Octa. Nona. If you're Italian, that's also what you call your grandmother. And deca. Sorry? No, yeah, that's your grandma. That's grandma. Well, she doesn't have to be 90. She can be just your grandma. My grandma's not 90. She's 86, but she's still my Nona. There you go. Oh, congratulations. Don't worry about it.
No, we have to worry about it.
I can't remember, so I'm saying don't worry about it, because what I mean is I don't know. So here we go. So, for example, what is H2O? Yeah, I mean, but what is it? It's water. But what's its chemical name? Well, how many hydrogens? 2. So I would call this dihydrogen. Dihydrogen. Then how many oxygens? So how do I say that? Monoxide. Yeah. So when you go to your tap and you open it up, you could go home and say, well, I'm just going to treat myself to a nice, cool glass of dihydrogen monoxide. And your parents will probably be like, no, don't. What did I do wrong? Now, there's a rule. This is weird. We never put mono on the first one, but it goes on all the other ones. I don't know why, but that's just a rule. So, for example, this one, CO2, it is carbon dioxide. Oddly, for whatever reason, we don't call this monocarbon dioxide. It's just, listen, the assumption is that you only have one of the first thing. So they only put mono on the other things. I don't know why, but that's the rule. But this would be what? Carbon monoxide. Good. What would H2O2 be? That's a great one. Now we call this, we have an everyday name for this, which is hydrogen peroxide, but its actual proper name according to this would be what? Dihydrogen? Dioxide. So really, you just use the prefixes and you change the ending of the whole thing to "ide," and that's it. Yes. Hello. Great. Perfect. Thank you very much. Sure, that'd be great. Yeah. I wouldn't drink it. I think so.
Yeah.
Yeah, I think Cassie talked me into 2.
Yeah.
Okay. Ruby, what are you doing? Stop being a menace.
Ruby's gone.
Ruby's speaking in the third person now?
Over here.
Ruby was here. Joe's not fooled. Okay. Okay. So, again, you don't actually need to know the naming in grade 9, but I just think it's helpful to know what to call these things. Does that make sense? So I'm not going to test you on the naming, but I think it's worth knowing. The naming? How about this? I'm going to give you a name and see if you can draw it. Let's go with... no, that's fine. Tetracarbon octahydride. See if you can tell me what that would be. Tetracarbon octahydride. Take a minute. Write down what you think.
Stephen already has it.
So do I.
I almost like it. I don't quite like it. Well, carbon and hydride. So what are the 2 elements here? C and H. Now what are the numbers? Tetracarbon means there's... Look up tetra. What's tetra again? Tetra is 4. Very good. So that's C4. And then octa is 8. Good. That's it. That's all there is to it. What if I did... silicon hydrogen trifluoride. Oh boy, that's tricky, but I bet you can figure it out. Silicon hydrogen trifluoride. Silicon, actually this should be mono. Whoops, pardon me. Broke my own rule.
Do we have to put a 1 there?
No, you don't have to write the ones. Though if you do, for the purpose of this course, I won't mark you wrong. Yeah, very good. Well, almost. S is sulfur, so I don't have that. S is sulfur. I want it to be silicon, not sulfur. Look, use the periodic table. Then look at that periodic table. See if you can figure out what silicon is. What would this be? What would this be? Oh, okay. There's a hand very much in my face, so I'm going to say your name so you'll stop doing that. Yes. Yep.
SHF.
I almost like it. What would the name of this thing be? This is close. What would that be called?
Sulfur.
Sulfur. Keep going.
Oh, sulfur.
Sulfur monohydrogen trifluoride.
Good. But I didn't ask for sulfur monohydrogen trifluoride. I asked for silicon monohydrogen trifluoride. So what's the only change I need to make here? Yeah, just like that. Very good. Okay. Does anyone have any questions about that? So now we've learned the 2 ways we can make compounds. We can give and take electrons, or we can share electrons. We're going to do lots of practice over this, but this is the last real major new concept. You've got some homework here. It's due tomorrow. You got a reprieve today, and you can thank Mr. Luciani for it. But I am going to collect Wednesday's homework, the 3.8 homework, tomorrow. So make sure that you have both done for tomorrow. Both. 3.8's homework, which can be found right here, and 3.9's homework. You got to have them both done for tomorrow, and I am collecting them. The other thing is that, so you can get going, you've got 5 whole minutes. That's good to get a couple questions done. Secondly, what do you have tomorrow?
A test.
No, not test, eh? A lab, so make sure you're dressed for it. The which?
I'm looking at you. Whole day not
Yeah, do you really want me to collect that? Because I will. But I'm not super keen to. Yeah, I mean, the truth is that was for your benefit. But yeah, I mean, again, if you really want me to, I will. Okay, but how they this is good. You know, how they actually. Okay, but how do they actually? I'm going to show and then maybe this hydrogen's going to have to be maybe drop where it's maybe over here. You know what I mean? Like you could drop it, but and then show me how it's electron.
Yeah.
Does that make sense? Likewise, maybe yeah, what else? Stuff that
I know. Oh, that's really loud.